Okay guys, so in the previous video I was talking about a family of triangles inscribed to a parabola, this green parabola here, and circumscribing a circle, okay, whose center is the focus of this parabola. Okay? So you can think of this object here as the circumparabola to this triangle whose focus is on x1. It's a well-defined object. Now, this is a Ponceletian family in the sense that this triangle family in its entirety is inscribed to the same parabola and circumscribes the same incircle. Now, what we're talking about in the previous video was that the orthocenter of this family had this curious property of actually being railed to an infinite vertical line. That's pretty cool. And here I'm actually showing the altitudes, since this family, I believe, is a family of obtuse triangles, right? Their orthocenter is always exterior. That's pretty nice. Okay, so I want to continue this exploration, and we're going to touch upon another very interesting family derived from this one. Okay, now just so we don't forget, recall I'm going to erase the x4 locus here and its altitudes. And I want to just remind everybody that this family can also be regarded as a family of tangential triangles to a bicentric family whose incircle passes through the circumcenter of the bicentric family. So I'm showing my auxiliary well-known n equals 3 bicentric, also known as puristic triangle. I'm showing how this family we're interested in, inscribed in a parabola, is nothing more than the family of tangential triangles to my bicentrics. Okay, so now let's erase the bicentrics and let's start approaching what we want to talk about here. So I have a little script here on my left side that I have to read. Okay, all right. So now I actually want to light up a very interesting derived triangle. I'm going to light up so-called polar triangle of the green with respect to this circumparabola. What does that mean? This triangle, this red triangle here, has sides which are bounded by the tangents to the green parabola at the vertices, meaning it's bounded by the polars of the vertices of this triangle with respect to this circumconic, the circumparabola, this green parabola. So if you take a vertex which is on a conic, the polar is simply the tangent. So this object here is sometimes called the polar triangle of the reference one with respect to this conic, the circumconic. So here's my polar triangle, this red object here. Now it turns out this red object is full of surprises. Okay, but before we actually get into that, let's just recall a well-known property of parabolas, right? If you take three random tangents to a parabola, random, they can be emanating from anywhere on a parabola. As you intersect those three tangents, they're going to form a triangle. They're going to intersect in three spots, A, B, C, and you can think of that ABC triad as a triangle. The circumcircle of that triangle necessarily goes through the focus of the parabola. So the focus of my parabola is the incenter of my tangential family. So when I draw this polar triangle, which is nothing more than the intersection of three not random but specific tangents, they're the tangents at the three vertices of this triangle, okay, but nonetheless they are three tangents, they're intersecting at the vertices of the red triangle. The circumcircle of the red is going to have to go through the focus dynamically. I'm not enforcing this, I'm simply computing the polar triangle and drawing its circumcircle. Okay, very good. All right, let's see, what do I want to show next? Yes, I want to show that this family is full of surprises. The first one, I'm going to light up the objects associated with this family. I just have to figure out where they go. Where would they go? So not that, not that. No, yeah, okay, before I go there, I actually want to talk about this. because this is a polar image of a triangle family, a Ponceletian triangle family, with respect to one of the conics, okay, it is a pretty well-known thing that this is also going to have to be Ponceletian. Okay, so this red family is also Ponceletian. It's actually inscribed in a hyperbola, which is the polar image of, and now I'm actually saying something wrong. Let's think about this. Is this the polar image of the inner or the outer conic? I believe it's going to be the image of the inner conic, right? Because the image of the outer conic, the parabola, is the caustic to this family, which is a parabola itself. This parabola is self-polar. Its polar image with respect to itself is itself. So you can see that this is a rather curious family of polar triangles. Its caustic is the original parabola. So it's a Ponceletian family circumscribing a parabola. This green object here is actually in parabola, fixed in parabola or caustic to the red family. And it's inscribed in the polar image of this circle, of the original caustic, with respect to this parabola, which is a hyperbola. Okay, I'm sure that we can work on some inversive geometry, and this is all classical stuff from the 19th century. Okay, so I have a family of triangles, which I had never examined before, inscribed in a hyperbola and circumscribing a parabola. Very interesting, right? So everything is very degenerate here. Very degenerate. Okay, so let me look at my scheme of things here. Let me hope I didn't throw anything away. Gosh, where would that be? No, that's not it. That's not it. That's it. Okay, it's poorly labeled. Okay, so I want to show you guys this phenomenon now. You can go through Kimberlin's Encyclopedia of Triangle Centers, and you can, pick a range of triangle centers from, say, 1 to 1,000, and you can query numerically the red family for any triangle centers that remain stationary over the family. Before I talk about these 4 stationary centers over here, let me actually point another phenomenon that is a little easier to explain and more fundamental. Here's the barycenter x2 of my red triangle, and here's the circumcenter, the center of this outer circle here, which passes through the focus. Okay. Now, this is the Euler line connecting the barycenter to the circumcenter. The very first phenomenon one notices is that the Euler line of this family passes through the focus of the caustic, this green in parabola here. Okay, so these two families, they're talking to each other in many different ways. This is the first one they talk to each other as. So we have an Euler line, a family of Euler lines, always passing through the focus of the original parabola. Okay. Now the second thing I noticed when I started to experiment with this was that there's a very curious point in Kimberlin's list, which I had not studied before, the 26th triangle center on his list, X26. And this center, just in a minute I'm going to tell you guys what this thing is actually computing the focus for us. So this is a center, a very curious center, that is not typically for a generic triangle on the circumcircle. It can be anywhere on the plane. But for this specific family of triangles, it's rather degenerate. Not only is it on the circumcircle dynamically, but it's actually on the focus of my original parabola. You can see this. So you take a triangle out of this family, compute its x26, and it sends you to the focus. What is x26 in Kimberlin's list? It's actually the circumcenter of the tangential triangle to a reference triangle. So I could actually draw that. This is not so germane. Is that the one? Yeah. So here's the, this is another family of triangles which I haven't studied yet, but these are the tangential triangles to my polar triangles. And here's the circumcircle of the tangential triangle to my polars. And its center, you can see here, just eyeball it, x26 is the circumcenter of this guy. And as you actually jog through the family, the circumradius of the tangential, the cyan triangles, they're changing, but the circumcircle remains centered and concentric with the original incircle of my green family. So you have two circles here that are concentric, but this is not germane, so I'm not going to spend any more time talking about tangential triangle to my polar. I want to talk about the polar triangle here. So there's three more points on the screen here which remain fixed at very curious locations, right? So the first one we just covered is x26. It's fixed on the focus. The Euler line is going through it. And then you have this pair of points here, x68 and x110. They actually fixed at the vertices of the hyperbola to which my polar family is inscribed. I have no idea why. Okay, and there's a third center in this range from 1 to 1000, which is also fixed. There could be more going down Kimberling's list. In fact, you actually want to derive what's the condition for a particular point to remain fixed, right? But there's another one called x161, and this guy here is fixed on the left edge of the original incircle. Okay, now I want to just say a couple of things here about x110. x110 is always on the circumcircle of any triangle. Okay, and it's also known as the focus of another well-known parabola known as the Kiepert parabola, which I can draw here. So there's an parabola. This is another parabola tangent to the three sides of this polar triangle, and its focus is over here. It's x110. Now, if I jog the system around, my Kiepert parabola is actually moving. Okay, but its focus is stationary. So this is kind of like a convention of parabolas, right? I have the original parabola, which is inducing this polar family, and this polar family has a stationary point, which is the focus of another parabola, another family of parabolas. What's the relationship between these two? What are loci, for example, of the vertex of this Kiepert parabola? We should study this going forward, but it's not exactly germane now, so I'm going to turn off this beautiful object, this beautiful family of parabolas, whose focus remains constant, stationary. Oh, by the way, the directrix of the Kiepert parabola is the Euler line. So you can go to Math World and check out what the Kiepert parabola is all about, but its directrix is precisely the Euler line. So there's another harmony. This parabola is talking to the original family via this family of Euler lines, which always goes through the focus. So this is pretty crazy stuff. You can see here that I'm actually drawing the axis of the Kiepert, and it's hitting the Euler line perpendicularly, and the vertex, which is slightly away from the red, from this red edge here, is actually the midpoint between x110 and this foot of the perpendicular onto the Euler line. Okay, still not the main thing here. I want to get to the main thing, and we're getting closer and closer to it. Okay, so let me go back to my script. Okay, so now we got to the first very surprising result. I actually want to show you guys individual loci. So let's go ahead and show the locus of x1. Yes. So here's the incenter of this family of red triangles. This incenter looks pretty straight, right? And actually fooled me. When I first saw this, I said, hey, I have another phenomenon. I have the incenter of a family similar to the orthocenter of the green, right? Not the same family here. Before I was looking at the orthocenter of the green family, which is over here, but I'm actually looking at the incenter of this red family, of this polar family with respect to the incenter-centered circumparabola of a reference family, right? So here's the incenter locus. And this thing actually fooled me before, because I looked at this and I actually told a couple of colleagues that this was a straight line, but numerically this is looking more like a very stretched out parabola, and the jury is still out. We don't know if this is a true straight line, or if this is if this is a very stretchy conic that looks numerically like a parabola. So we're actually saying that the locus of x1 is either a straight line or a parabola. But let's go to x2, which is already lit up over here. Let's go to x2. Now x2 is actually a line. Okay, this guy here is a straight line. So not only is my Euler line, which contains x2, going through the focus, but x2 itself is actually moving along a straight line. How about x3? Same thing, also moving along a straight line. Now if x3 and x2 are moving along a straight line, everybody who is on the Euler line, any point that is on the Euler line at a fixed which is a fixed linear combination of x3, and x2 is also going to move along a straight line. Okay, but actually, let me actually get to the point. There's a bunch of triangle centers of the polar family who move up and down along an infinite straight line over the red family. And I'm going to light up for you guys a few of these, maybe 20 of these. So I'm going to turn this guy off, and I'll say, show me all the loci. So here we go. So we have this barcode Frankenstein family, right? Where dozens of, so I'm counting here on my script, there's maybe 20 or 30 triangle centers between x1 and x200, whose loci over the family is an infinite straight line. I personally had never seen anything like it. So you can see here x64, x110 itself, which was that, actually x110 is fixed, so actually I'm showing the fixed guys here as well. I think I can take them out. Let's see here, can I turn them off? I want to turn off the fixed guys. Yeah, here I'm turning off the fixed guys. Now I'm only going to show the triangle centers whose loci are actual proper straight lines. So I got x64, x66, and I can jog my Poncelet family. And you can see here that mysteriously, a lot of these centers, and not all of them are on the Euler line. You can see here that there are centers that are not on the Euler line. The psi-median point is one of them, not on the Euler line. You got x74 on the circumcircle, not on the Euler line. x67, not on the Euler line, and so forth and so on. There's, in the first 200 Kimberlin centers, there's about 20 to 30 of those. I've never seen anything like it. So I have a family that is not a translating family. This is a proper Poncelet family of triangles with dozens of triangle centers simultaneously moving along straight lines. So this is very degenerate. Okay, let me look back. So I'm calling this the barcode or Frankenstein polar family. Okay, so here's the next topic. I now want to show you guys certain triangle centers whose loci are circles. And another surprise happens. So there's several triangle centers whose loci are numerical circles. So here's a few examples. X99 is the first one I actually ran into. Let's look at X99 before I show you guys the whole list. Let's take this out, and I'm going to say X99. Let's go X99. Should be here somewhere. So here's X99. Yes, so the locus of X99 was the first one that caught my eye. Recall that X99 is known as the Steiner point. It's the intersection of the circumcircle of a reference triangle with its Steiner ellipse, right? This is not germane, but what is germane is the fact that this very interesting point is describing a circle. You got this little gap here because I'm avoiding certain regions here where the original triangle becomes unbounded. So, but the circle actually closes and it's bounded. Maybe it's not defined at a particular location, but it's a circle. Minus a point, maybe. So X99, the Steiner point, is a circle. You can see that the circle is tangent to that vertex, which is the focus of the Kiepert parabola. Let's bring back the Kiepert parabola. So the locus of X99 is tangent to the fixed focus of my moving set of Kiepert parabolas. Okay? All right. So then I can bring up a collection of such points, such triangle centers, whose loci are circles. And then you notice another thing. It looks like, at least from this range that I checked, I think it was k equals 1 to 1,000, the first 1,000 triangle centers in Kimberlin's list, you verify an interesting phenomenon. Okay? Let's actually scale this out. Can you guys see what's going on here? Many of these points, and I'm not sure if all of them, doesn't look like it's all of them. There's one here that is not the case, 249 and 90. But many of these points lie on the circumcircle. Many of them. Okay. Now, maybe 249 here in the middle does not. Let's expand this a bit. Here's 249, does not lie on the circumcircle. But all the other ones, 476, 691, 925, this dash red thing here is a circumcircle, right? So let's jog this family just a little bit, so we can see that. All these guys, including the focus of my original parabola, lie on the circumcircle. And except for a couple of, maybe there's more, but I'm seeing an exception here, x249. I don't know why this guy is not, but we should investigate that. But the other thing that you notice is that all the loci pass through x110, the focus of my Kiepert in parabola. So this is a parabolic pencil of circles. Remember, you have different pencils of circles. You can have circles that don't touch, then you have two sets, and they're sort of disjoint, so you can call that perhaps a hyperbolic pencil or elliptic, depending on the definition. There's a different kind of pencil where the circles actually have two common points that they pass through. And this is the family, this is the type of pencil that is between the hyperbolic and the elliptic pencil, in that all the circles in the pencil have a single common point. And this, I've seen this referred to as a parabolic pencil of circles. So, very strange stuff. I started with a green parabola, okay? I noticed that one of the stationary points was x110, the focus of the Kiepert in parabola, and then I noticed that all the centers whose loci are circles are members of a single parabolic pencil. So this is a convention of parabolas of sorts, right? Okay, let me go back to my script. Okay, x1. I think that this is it, right? Is there anything else that I wanted to show? Gosh, I've showed, I think, most of the things that I wanted to cover. So I think I'm going to stop here. Thank you very much. Just feel free to send me any comments or any ideas, any proofs, any insights. I really appreciate it. I'm just kind of learning about this as I go. But this looks like a very interesting family of triangles. One of the things that I would love to try here is what's the locus of the vertex of the Kiepert in parabola over this family, right? It's probably going to be a very pleasant curve. Maybe it's a straight line as well. Yeah, so I think that this is pretty much it for this video. See you on the next one. I'll leave some information in the description. Thank you.